that an experimentalist will do to exhibit this phenomenon is the following. So here is the time axis. Time will be measured on scale Cn. At time 0, the experimentalist prepares the sample of matter in a certain state, in an initial state, and then it lets it evolve by itself.
Which is the scale?
Sorry?
Which is the scale?
The scale? I call it right now Cn. This is the time unit. So I will, it's just an introduction. Everything will be made precise later, okay? So the experiment is you prepare your system in a certain state and let it evolve by itself up to a certain time, tw, and at tw, the experiment begins. The experimentalist will probe the system, do a measurement of some observable quantity that characterizes its state. Okay, it does that, then waits an extra time t, and at time tw plus t, you measure how much the system is correlated to the state it was in at time tw. So what the experimentalist measures is a time-time correlation function. So this is a function of the two times, tw and t, the duration of the experiment. Now, if the system were in equilibrium, so suppose that the system is in equilibrium, then what you would get is that c of t and tw is or behaves like a function of t only for at least tw and t large enough. Plus grand? You can't read, it's too small? I will try, okay. So if the system is in equilibrium, what this means is that it becomes time translation invariant. It will depend only on the duration of the experiment. Now, this is not what happens in glasses. In glass, we are out of equilibrium. So I'll write bigger. In this case, our two-point function, c of tw and t, behaves like a function that is a function of a single variable, but it is a function of the ratio of tw to t. And this function f behaves like this. So when tw is small, so I should rather write t over tw, okay? So when t is small compared to tw, the correlation is strong. The system remembers its past, so f is some big constant, say 1. And on the contrary, when t becomes very large compared to dw, this ratio goes to infinity, and the correlation decays to 0. So this is not surprising in itself, it's normal. But what is remarkable here is that the time it takes for the system to decorrelate is roughly proportional to tw. So the time it takes the system to forget the state it was in at time tw is proportional to tw. So this is one of the main observations. And the second important observation that physicists do is that this happens on all laboratory timescales. which means on all time scales ranging from seconds to minutes to hours to hundreds of hours and so on, they will observe always the same limiting function. So this means that the process never reaches equilibrium, but it becomes slower and slower as time goes by because it decorrelates from longer and longer TW periods. Okay? So this explains what physicists say, that these glosses are never observed on equilibrium, even on geological timescales. So to understand how, so this was known for a long time, but to understand how to model this on a theoretical point of view took a much longer time. It is quite recently, in the late 80s, beginning of the 90s, that the realization that materials that had recently then been discovered in physics, called spin glosses, were good models of aging of glosses that sparked a renewed interest in this phenomenon. And they, so this spin glosses were first found experimentally. They are real materials, and they were modeled from the viewpoint of theoretical physics. And several models were proposed that are that have been studied in probability theory as well. And most of the focus then was on the statics of these models, these mean field spin glass models. And then they discovered that they were good models to model this aging phenomenon. So in this lecture, I will present these models. So perhaps So I will organize these lectures in essentially one model per lecture. So today will just be an introduction. Tomorrow we will see the trap models. The day after, the random energy model, which is the simplest of all mean field spin glosses. Then the phase spin model, and again the RAM, but from a different viewpoint. So I will now introduce the abstract setting in which all these models can be formulated, which is the setting of Markov jump processes in random environment. So the models that I will later introduce can be formulated inside this setting. So given an integer, I will denote by Gn a graph with set of vertices Vn and set of edges En. So this is a sequence of graph. We will assume that the size of the graph diverges, but I do not exclude that Vn is V infinity, for example, Zd. On the graph, we will construct a random environment which I will also call random landscape. It is a collection, tau and x, of positive random variables attached to the vertices of Vn. And since we'll later be interested in taking limits as n goes to infinity, I shall construct the whole sequence of random landscape on a common probability space. So defined on the common probability space that I'll call omega f blackboard p. Then on this random landscape, we consider a Markov jump process. Xt, which has an initial distribution mu n and rates. So the rates are denoted lambda and x. It is 0 if xy is not an edge of the graph. And otherwise, it obeys a detailed balance equation with respect to tau. So tau n x lambda n of x and y is equal to tau n y lambda n of y and x if x and y is an edge of the graph. So this implies that the process xn is reversible with respect to the measure. So x is reversible with respect to the measure that assigns to x the mass tau n x. So in particular, all Glauber dynamics fall into this class. I will come back to this later. So now there are two ways to characterize the law of the process xn that you learned in school. The first way is through the infinitesimal generator matrix. So this is the matrix with of diagonal elements the rates, lambda n of x and y, and diagonal elements, lambda xx equal to minus lambda x, where lambda x is the sum over all y such that x and y is an edge of the graph of the rates lambda n of x and y. So this is the first way to specify your law. The second way is through the jump chain and holding time description of the process. So what is this? The jump chain I will call it J and I, is a discrete time Markov chain. So discrete time Markov chain on Vn with one-step transition probabilities. Little p of x and y, given by, should write a little bit. The ratio of the rates, lambda n of x and y, to, so precisely this diagonal element, lambda n of x. So again, this is if x and y is an edge of the graph and 0 else. So this jump chain describes the trajectories of the process xt. Now, at each step of its trajectory, the process will wait an exponential holding time. So, is it big enough? Can you see it from the bottom of the room? So, okay. So so the holding times so at each step of the jump chain, Jn1, Jn2, etc., the process xn waits exponential holding time with parameter lambda n of minus 1 j n I times an exponential random variable e n I, lambda n minus 1 of jn2 times an exponential random variable an2, and so on and so forth. So conditional on j, these holding times are independent exponential random variables. Now, we use this jump chain and holding time definitions to construct a clock process. The clock, Sn, is the total time spent by the process Xn along the trajectories of the jump chain. So Snk is the sum from I equals 1 to k of the mean holding time lambda n of minus 1 of jni times eni. So the e's here are exponential, mean 1 exponential random variables. So that is the total time spent by the process along the first process xn along the first k steps of its trajectory, so along the first k steps of the jump chain. Okay, now we see that if we inverse this clock and use it to time change the chain Jn, then we get back our process Xn. So this is to say that Xn of t is equal to Jn of I for all t between Sni and Sni plus 1 for some I. So if t is in this interval for some I. And it is, so I like to write it in this way because we understand what we do, but most of the time we write it in this way. X is j and time changed by the inverse of the clock process. And the clock here, of course, cannot be inverted in the usual way because it's a step function with flat parts and discontinuities, so we have to use a generalized inverse. So this is the notation for the left continuous generalized inverse of such a function. So this gives us a second way to define our process, and I guess you studied the two possible definitions when you studied Markov chains. Now, this will be very important to us, and I just want to make a short remark that will be useful in our last lecture, is that I could also have decided to define my process differently. If, namely, I can define it as the time change of any Markov jump process that has the same jump chain as Xn using some appropriate clock process. So here, Y is another Markov jump process that has the same jump chain as Xn, but a different clock. And then you have to play a game. What is the most useful representation for you to get the result you want to get? Okay, so this is just a small remark, and I will come back to it in details in the last lecture. So there are lots of probability spaces in these lectures. So let me just fix the notation. They will stay the same throughout the entire lecture, so we should not get too lost. So all these processes are sequences of processes, and I will always construct them in a big probability space. So the probability space of the process Xn will be called omega x. Its algebra fx, and its law is calligraphic p. So this is the probability space on which x is defined. In the same way, I will call omega j, fj, and so the ordinary p for the probability space of the jump chain. And I already wrote down that omega f blackboard p is the probability space of the random environment. So of course, these two processes are random variables on this probability space. So you see they are reversible with respect to my taus here. So the law depends on the random environment. And depending on my model, the law of the jump chain will or not, as we will see, also depend on the random environment. So when I want to specify that I fix a realization of the random environment, that is that I condition on a certain event in my sigma algebra here, I will add the superscript omega, and I hope I will not forget to do it. When I want to specify the initial distribution, mu n, I add it as a subscript. And in the same way, I write calligraphic E mu n for, and calligraphic E for short, for the expectation. And the same for the law of J, so I will write P omega to specify that I fixed a random environment, P mu n to specify and E mu n for the expectation. I think this is it for the notation. So I will now introduce the main models that we will be interested in these lectures. So I told you that that this started with when physicists, this outburst of research activity on aging started when physicists became aware that mean-field spin glasses were the right framework to formulate the aging problem for glasses, and but they never studied spin glasses themselves because these models are mathematically too complicated. So they proposed many simpler models, and one that became extremely popular is trap models. So it's not one model, but a whole class of model. And the first one was proposed by Jean-Philippe Bouchot. So there are several trap models. In the lecture notes, I defined them in some generality, but let me start with a simpler one, which was the original choice of Jean-Philippe Bouchot, which is called the REM-like RAM-like trap model. So in this model, so now we have to specify all these quantities, the graph, the random environment, and the dynamics. In this model, the graph is a complete graph on n points. So Vn is the set of the first n integers. And G is the complete graph on Vn. The random environment, tau, is made of IID random variables that are in the domain of attraction of a stable law of exponent alpha. So they are always positive random variables, IID positive random variables. So this means that the probability that tau is larger than u is equal to u to the minus alpha times L of u, where alpha is a parameter in 0, 1, and L of u is a slowly varying function, which means that L of tu divided by L of t goes to 1 as t goes to infinity. So you see in particular that these variables have infinite meaning. Okay. And now we have to specify the dynamics. So if I use the infinitesimal generator description, so the jump rate description, the lambda n of x and y is equal to 1 over n tau x for all y such that x and y is an edge of the graph. So this process jumps from x to y with the same jump rate regardless of the landing point. In terms of the jump chain and holding time description, the jump chain, Jni, is the simple random walk on the graph. On Vn. So it means that it jumps from x to y with a probability 1. So yes, 1 over n, and at every x, it waits a holding time with parameter lambda n minus 1 of Jni, or say lambda n minus 1 of x, is equal to tau n of x. So this the way this chain behaves, so if I represent the graph, the endpoints of the graph in this way, then the process starting in a given point x will wait there an exponential time that depends on tau n at x. I should not put an n because it's really not a function of n, so I sometimes do it just out of the habit, but okay. So it waits at each site x an exponential time of mean value tau x. So it's called trap models because we imagine that at each of these sites there is a trap that the process gets stuck in. That is, and the taus represent the depth of the trap. So once in x, it waits a time that is proportional to the depth of the trap at x. And when it jumps, it chooses one of the other sides uniformly and jumps there with a uniform probability, regardless of the site where it starts from. So this is the simplest model of aging. And this simple model was proposed as a kind of caricature of what physicists expected the aging behavior of the random energy model, which is a spin system, a microscopic spin system, would behave. So this is the simplest one. Then there were very many trap models that were introduced by Bouchot himself. So another one is the Graham-like trap model. Here, in the Graham-like trap, you construct it in this way. You take a rem, so the same graph as in the rem, your endpoints. And to each of the vertex of your graph, you attach another complete graph, and so on and so forth. And in this way, you build a hierarchical tree on which you construct your landscape. And then you set up a dynamics that is on the leaves of the tree. At each leaf, the process waits. And when it jumps, it will go up in the tree and then go down in the branch that descends from the point it reaches with a uniform probability, and it goes on jumping like that. And this little model is supposed to be representing dynamics on what physicists call the Parisi tree of the spin glosses that represent the equilibrium property of the model. So I will not introduce this model. There is another question that has received a lot of attention, which is the question of how to construct a limiting dynamics from this model. It's called K processes. It has been initiated by Luis Renato, I guess, Fontes. And I know that lots of people in Rio has been interested in these models as well. So it is one big question. Other models of trap models are models on ZD. So you define them in the same way as the REM-like trap model, but you replace your state space by ZD. So, and then there is another kind of dynamics that has been introduced because, as you can see, this one is rather simplistic. The transitions are made regardless of your landing point, and this is totally absurd from a physical point of view because you expect in real physical life that the jumps will depend on the entire landscape, not only where you are, but on how difficult it is to get where you want to get. And there are other choices of the rays that are called the asymmetric REM-like trap model that try to take this into account. But it's, how to say, from the physics point of view, these models have a big defect. You don't know what it means to put a magnetic field, so it's difficult to completely give a physical meaning to a jump that would depend on your landing point. It was a big obstruction in some sense in the physics of the problem. So let us go and see what are the microscopic min-field spin glass models that these trap models were proposed to describe. They were introduced about 20 years before track models were introduced. So these are microscopic spin systems. The state space here is the n-dimensional discrete cube, minus 1, 1 to the n. And the graph is the set of edges of the cube. So in statistical mechanics, a model is described by its Hamiltonian. In classical statistical mechanics, the Hamiltonian is a deterministic function on your spin configurations. In min-field spin glasses, the Hamiltonian is a random function on this space. So the random Hamiltonian I will call it H and X. This random Hamiltonian is a stochastic process. It is a Gaussian process. With covariance, so it is a centered Gaussian process. With covariance of the form n times a certain function of the overlap between x and y. So this quantity r is called the overlap. So this space is our spin space. So x belonging to that space is a sequence xy to xn. It is called a spin configuration. And one element xi of this sequence takes value minus 1 or plus 1 and is called a spin. Okay? So this overlap is 1 over n, the sum from I to n of xi, yi. It is the inner product of the two configurations x and y. So this, and f is a function. So here f, it is a smooth function with, that satisfies f of 0 is 0 and f of 1 is 1. So we see that I can also express the overlap as a function of the Hamming distance or the graph distance as 1 minus 2 over n times the distance between x and y, where the distance, the graph distance here on the hypercube, counts the number of components of spins xi that of x and y that disagree. So each time you have a spin that disagree, you add 1 to your distance. So, so this is a generic way to define this family of min-field spin glasses. Now, different choices of the function f will define different models. When f of r is the indicator set of r equals 1, we have defined the random energy model. This model was, so almost all the models that I'm going to write down are due to Bernard Derrida, except for one. So I will tell you which one is not, was not proposed by Derrida. So we see in this case that the covariance matrix becomes simply a diagonal matrix with n on the diagonal and 0 as off-diagonal elements. So here, Hn of x are IID centered Gaussian random variables with mean, so 0 invariance square root n. So this is the simplest model, a collection of independent random variables. Then this is the simplest, and the hardest is the SK model. SK is for Sherrington and Kirkpatrick, where they proposed to take the function f of r to be r squared. So in fact, this model was proposed first, and all other models were proposed as simplifications of this Sherrington and Kirkpatrick model. The base spin SK models, base spin SK, where P is between 0 and whatever, is obtained by taking f of r as the function r to the power p. So what happens is this model was proposed first with r squared, and people quickly realized that it was very difficult to understand this model because it is a very strongly correlated model with a correlation structure that is rather mysterious. So they proposed a model. So you see that if you take P large and insert this into your definition of the covariance, so if I raise r to the power p, I see that the larger, so if I do this, I raise r to the power p. Now, if I take p very large, I see that my off-diagonal elements of the covariance will tend to become small, and the largest element will be on the diagonal because this quantity is smaller than 1. So you have 1 minus something smaller than 1. When p becomes large, it drops to 0. And in the limit, if you take p goes to infinity, then all elements will be 0 except the diagonal elements, and you get the rem. So this P-spin SK model was proposed as a family of model that interpolates between the SK model and the random energy model. You will ask me then, why do I still distinguish P-spin from SK? It's because indeed it was discovered that it doesn't really interpolate it, and that the SK model remains strikingly different in its behavior from any P-spin SK model. So the P-spin never are approximation of the SK model. So this is for the little history. So you also can represent the Hamiltonian of the SK model and of the P-spin SK model in a classical way, using spins as the sum over I, so I1 up to IP of correlations Ji1 IP x I1 x IP with a prefactor here and to the square root n to the p, where these j's here are IID standard Gaussian random variables. So this is an equivalent description of these Gaussian processes as the one I gave here. So these are the models that we will be interested in. Now, what are the dynamics that we will set up on these models? generally speaking, the dynamics we will be interested in are Glauber dynamics. Glauber dynamics are any Markov jump process that is reversible with respect to so any x and t, Markov jump process, reversible with respect to the Gibbs measure, of the model. And Gibbs measure is the measure g beta n that assigns to x the mass, so exponential minus beta h of x divided by z beta n, where z here is a normalization that makes this a probability mass, and beta is the inverse of a temperature. So to use always the same notation, I will write exponential minus beta h of x as tau and x. This quantity here in statistical mechanics is called the Boltzmann weights. So g beta n is the ratio of the Boltzmann weight at x divided by the sum of all Boltzmann weights over Vn. So any Glauber dynamics in principle is a good dynamics for the model. The most used one is metropolis dynamics. I will not define it today. I will do that in the last lecture because it's in the last lecture that I will discuss this dynamics. It turned out to be difficult to study this dynamics, and the first results are in fact very recent. The dynamics that received the most attention is a simpler dynamics called the random hopping dynamics. And the random hopping dynamics is essentially a trap model dynamics. The jump chain here is the simple random walk. The simple random walk on the hypercube. On Vn. So as in the trap model, the walk does not depend on the random environment. A simple random walk takes a step uniformly from it. It chooses uniformly from its nearest neighbor the neighbor where it will next go, and it does that with a uniform probability. So it's really like in the trap model, and it waits. And it waits at each site with a holding time. Again, with a mean holding time equals to tau and x. So this process now lives on a big hypercube, but when it is at a given site, it waits there an exponential time of mean value given by the Boltzmann weight at x. And when it jumps, it takes one of its nearest neighbors in the hypercube and choose one with probability 1 over n because it has n neighbors and goes on this way. So this simple dynamics has allowed to understand many things about aging in these models, and it was a very, very useful dynamics to study. So we will, in the next lectures, start with the REM-like trap model, then, the REM-like trap model, then the random hopping dynamics of the random energy model, the random hopping dynamics of the p-spin, and then metropolis dynamics of the random energy model. So I would like now to come back to our initial aging experiment and see how we can formulate it now that we have a mathematical framework to do it. So just check time. So what about aging now in this framework? So if we remember our experiment, we know that we have to choose 3 ingredients. The first is a time scale. The second is an initial distribution. And the third is the 2-time correlation function that we want to study, on which we want to observe the aging phenomenon. So from now on, will use the acronym 2-time correlation function, TTCF. So the choice of this correlation function will, of course, depend on the model. In trap models, the most studied quantity, the one that was introduced by Bouchot, is, so it is a function of the 2 times, TW and T. So you remember the experiment. We start in 0, wait up to TW, wait an extra time T, and at time TW plus T, we measure the correlation. So the quantity that was used by Bouchot to measure the correlation is the probability that, starting in your initial distribution, the process at time x TW and at time x TW plus S are in the same state for all S in 0 T. So let me read this again. So the process remains in the same state in the entire time interval TW plus T. So it means that the process does not jump in the entire time interval. And I forgot here to write that time is measured on scale Cn. So there is a Cn in front of little t. Another correlation function that has been studied is the probability of the event that the process is in the same state at this time and this time, but you don't want to know what happened in between. So in fact, we can ask for a milder event to occur, and use some distance and say that we want that the distance between the process at time c and t, w, and the process at time c and tw plus t remains small for some positive small epsilon. In particular, in the P-SPIN-SK models, one two-time correlation function that is particularly meaningful is to take this distance as the graph distance, because it is the overlap between the states of the system at these two time points. So we will ask that the overlap between the states of the system at these two time points remains large in the entire time interval. So, so you see that we have some choice in the choice of our two-time correlation function, but the idea behind the aging phenomenon is that, in fact, all these correlation functions that we can write, they will be we will be able to reduce them to a leading term that will be exactly the event that the process did not jump in the entire time interval. And this will happen when our processes are such that in the random landscape, the very deep traps where your process spends all its time, when they are very, very deep on long enough time scale, and when they are scattered enough, so that really the best strategy for your process to realize such an event is to stay where it is, or stay very close to where it is and not move away. So this will indeed be what we will always, at least this event, the event to which we will always try to bring ourselves to. So let us take a closer look at this event. We can write it in a slightly different way. We can write it as the probability that the range of the process x, so sorry, the range of the clock. So is the clock? Yes, the clock is still on the blackboard. I will need room. So let me call the range of the clock the set of points S and K. All possible values of your clock are rescaled on scale Cn. So this event here can be rewritten as the probability that the range of the clock process does not intersect the time interval tw plus t. This is an equality. Okay, so then this places your clock process in the limelight, because this probability now really only depends on the process through the clock. So if aging must occur, it must be some property of your clock or some property of the range of the clock. Now, we see that clocks are sums of random variables. They, of course, are not simple random variables. They are correlated in several ways. They are correlated through the process, Jn. They are possibly correlated through the random environment. But they are sums of random variables, and these have been well studied. In principle, we can expect some kinds of limits, and among the known limits that we can expect to get are subordinators. Why so? because for subordinators, we know that if I call R the range of a subordinator, I know that the probability that the range intersects a time interval, does not intersect this time interval. We know that this is a function of the ratio of TW plus T. This is a classical theory about stable subordinators. I'm not telling you today what this function f is, but I guess a number of you know. And so this happens because subordinators are self-similar processes. Now we see that it is this precise behavior that we want to get to show aging. In fact, this function f here behaves like, so when t, so I think it is t over t to tw, so when t is very small compared to tw, this function f behaves like 1, and when t is large compared to tw, it decays like it's the contrary. I'm getting confused. So I think it is tw here, sorry. So when tw is large compared to t, so we still are correlated, so we are close to 1, and when it becomes small compared to t, then it decays like a polynomial function of t, so minus 1, minus alpha. Okay. So this was just to make the link with the rest of the lectures. We have in mind that if we can show that our clock processes converge to subordinators, then there's a good reason why aging should occur, because precisely the correlation function that we are after would have the right behaviors. And so this pattern, so I think I was asked to stop at noon, so I will just conclude with a little bibliography. So the first connection between trap models and microscopic dynamics of actual spin system was so a little bibliography was obtained in a joint work with Gayrard Ben-Arous, Anton Bouvier, and myself. So it's a series of papers from 2003. This particular viewpoint, point of view based on clock process, was introduced and advocated by Gayrard and Ergigiani in a paper of 2008, and this was for the random hopping dynamics of the RAM, and this also was for the random hopping dynamics of the RAM. It was then extended to the P-spin-SK model by the same authors and Anton Bouvier in 2008 as well. Well, you can count 2006 because that's when the preprint was. It feels a little bit bizarre because then it depends on how long it took to publish your paper. But the preprint was from 2006 and this one from 2008. And then the techniques that I will show you were developed in a series of papers, so my papers and my joint work with Antoine Bouvier, where we will see that introducing there are some very efficient techniques for proving convergence of point processes in random environment that will enable us to improve all earlier results, and that have been applied to a large number of models now with success. And it will be nice if you are the young students would at least understand well the simpler models where these techniques are implemented, because then you can go and take your model and implement them for yourself and see how it works. So I had planned in the first lecture to do a lot more, but I will not have time to. So I will send the manuscript to Claudio Landim, who will make it available for you. So what I wanted to do was really remind you of what we need to know about point processes and Levy processes and subordinators. So I'm pretty sure it's things that you saw in your classes already, but it's nice to have them fresh in your mind. So if you have time, you can look up the appendix of the lecture notes, and so you're ready to listen to the next lecture. I think I will stop here.
Are there questions? No? So let us thank Véronique again. I would like just to make a couple of announcements. Okay, so who is interested in the boat trip, please confirm until tomorrow downstairs with staff in the lobby with staff from IMPA there. For those who are staying in the Hotel Everest, there will be a van going back at 7:30 p.m. So if you are planning to stay longer or you are not going back with this van, please let me know so that I can